Welcome back, AP Statistics. This is an additional topic. We're going to be talking about factorials, permutations, and combinations. You may be familiar with those concepts before if you've taken my pre-calc class, but if this is all new to you, that is great as well. Definitely a topic you want to know for the AP test. So let's talk about factorials first. If you want to find the number of ways of ordering n objects of any kind, you would find n factorial. N factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down to 2 and 1. And there you go. You count down from n to 1 and make a bunch of factors, things you're multiplying, hence factorial. Okay? So that's what a factorial is. It counts the number of ways in which you can order a set of n objects. For example, if you have 4 different objects and you want to find the number of ways you can order those 4 objects, it would be, well, your first object in line, you have 4 options. And then for your second object in line, you would have 3 options. And then you would have 2 options for your third object, and then you have only 1 object remaining, so there's your last option. So there are 24 ways of ordering 4 objects. However, it gets a lot more complicated from here. If you want to find the number of ways of ordering n objects in groups of r at a time, so you're not ordering all of them anymore, you only want to order groups of r at a time where r is typically smaller than n. All right, if r were the same size as n, you'd be finding a factorial, and I'll let you think about why that's true. But this is called, in the general sense, a permutation. Now, a factorial is a variety of permutation. It's the most simple variety of permutation, but generally speaking, a permutation takes n objects and says, how many ways can I group them in size r groups, where r is typically smaller than n? And this would be n factorial. You want to order all the objects divided by n minus r factorial. Now, why this denominator? Well, if we want to count the number of ways of ordering objects, all of them, that would be n factorial. But I don't care about the n minus r number of objects. I care about the order of the r objects I'm considering at a time. So the other objects, which would be n minus the r objects I care about, I don't care about the order of those objects. So I order everything, and then I unorder all the objects that I don't care the order about. Okay? So if ordering things involves multiplying, then I want to do a bit of division to unorder those things, since division is the inverse of multiplication. All right, so this is not hocus pocus. That's how the formula works. We order everything, and then we unorder via the inverse process, division, all of the objects that we don't care about ordering. So, for example, the number of ways to form a batting order with 13 players on the roster is 13p9. You have to have some baseball context for this. A batting order consists of 9 players. Say you have 13 on the bench. How do you form a 9-player batting order with 13 players? Well, it's 13p9. I have 13 players to work with, and I want to see how many ways can I order groups of 9 at a time. If I were to put those batters in a different order, that would constitute a different order of the batters. So each different order counts, but only of groups of size 9, not all 13 objects like we were working with originally when we were doing factorials. There's another way in which we count things, and that involves simply choosing. If you want to find the number of ways of choosing R objects from a group of size n, you would find NCR, which is equal to this mess over here. Now, what is going on here? Well, I start by ordering all of the objects, and that involves multiplication. But do I care about the order of any of the objects? No, I am simply choosing them. The order does not matter. So I want to unorder the objects I don't care about, and I also want to unorder the objects I do care about. Okay, because I'm not ordering anything, I'm simply choosing. Now, does this denominator entirely negate the numerator? Actually, no. What we have is the number of ways we could choose groups of size R out of a larger group of size N. Okay, and we're just choosing smaller groups from a larger group. How many ways can we choose smaller groups from a larger group? So the order in which we choose the R objects at a time does not matter. Okay, it's not like batting orders. It's not like you have your leadoff batter and then your second batter and your third and then your cleanup. No, it's not like that. The order doesn't matter in this case. So we want to unorder what we don't care about, obviously, and then we want to unorder what we do care about as well. We do all of that with division, the inverse of multiplication. So, for example, the number of ways of choosing 3 baseball bats from a collection of 7 is 7 choose 3. The order in which I choose those bats does not matter. So I would use combination. So let's do some practice problems, shall we? Find the number of ways you could order the letters of the word faith. All right. So how many ways can you order those 5 letters? Well, for ordering all the letters, it's going to be 5 factorial. 5 times 4 times 3 times 2 times 1, which is 120. Here's a more challenging problem. Find the number of ways you could order the letters of the word mathematics. Now, just looking at that word, we see it's 11 letters long, so we think it's 11 factorial. But hold on, there are some repeating letters. The M's repeat. So there are 2, or really, if we're going to be generic, 2 factorial ways in which I could rearrange those M's, and I'd still have the same spelling. I could put this M here and this M there, and it'd be the same spelling. Same with the A's. There are 2 A's, so there are 2 factorial orders of those A's that would produce the same spellings, as well as the T's. There are 2 factorial T's, ways I could order the T's, rather, that would produce the same spelling. So if I have repeated letters, here's how I handle that. I find the number of orders for all the letters, and then I acknowledge those doubled letters. If I have 2 of a letter or 3 of a letter or 4 of a letter, I do that number factorial and I divide it out, because if I were to switch or reorder those letters, I'd have the same spelling, okay? I'd have the same order of letters if I switched doubles or triples or whatever. So for the 2 M's, 2 factorial, for the 2 A's, 2 factorial, and for the 2 T's, 2 factorial. I divide all that out so I don't run into the issue of, oh, if I switch these 2 M's, I have the same spelling, but I'm treating that as different spellings. That'd be silly. So dividing all those double letter situations out, I would have this number that is nearly 5 million, which is how many subscribers I'm going to have eventually. You just wait. All right, so number 3, find the number of ways you could choose 7 players to form a team for a pickup game of football out of 12 kids in the neighborhood. All right. So I'm just choosing 7 players from 12. The key word here is choose. I don't care about the order in which I select these kids. I'm just choosing them, right? So that would be 12 choose 7, or 12 combinations of size 7. All right. 12 individuals, and I make combinations of size 7. How many ways can I do that? Well, that'd be 792. And I can show you how I got that number using the calculator. So we're back at the calculator. Let's get to work here. We're going to go to math, and we're going to go over to probability, and we'll see the notation for NCR, NPR, and factorial. So this is our one-stop shop for counting. We're going to go to NCR. Let's see how the interface works on this calculator. So this calculator automatically puts answer over here. It thinks that we want to use the answer to our last problem as our value for n, but in fact we don't. We're going to put a 1 and I'll need to insert a 2. So 12, NCR 7, and then we go down, hit enter, and bada bing, bada boom, 792. On to the next problem. A company has 6 photogenic employees. 3 of them are selected to be in a photo for the company's advertisement. How many ways could the 3 of them be ordered in the photo? And there's a key word right there, if there ever were one. Ordered. So order does matter here. We're not simply choosing like we were before. We are ordering people. It means the order matters, all right? And we're assuming they're standing in a row and facing the camera. So we're rearranging the order of the 3 that we select from the 6 in a row. That would involve a permutation, not a combination. We would want 6p3 equals 120. Now we'll do that on the calculator to confirm. Back to the calculator we go. We're going to go to math, go to probability, and we go to NPR. We're going to go say 6, NPR 3. So we have 6 for N, 3 for R, and we hit enter, and we get 120. So now a few problems for you to try. Suppose a department store employee had a collection of 10 festive outfits. How many different groups of 7 outfits could the employee choose to wear on their shifts on the week of Christmas? All right, so a festive question here. Try this one on your own. See if you got it. Okay, I'll assume we're ready to continue. The answer would be 10C7, which works out to be 720. You can confirm that on the calculator. Next problem. In a race featuring 15 horses, find the number of possible finishes for all 15 horses. Now, a finish in a horse race is the order in which the horses finish the race. So first place, second place, all the way to dead last. All right, so try this problem on your own. See how you do. Check your answer when you're done. Okay, I'll assume we're ready to continue. Here we go. 15 factorial, which is that absurdly large number. That would be thousands, millions, billions, trillions. So over 1.3 trillion finishes for those 15 horses. It's amazing how much factorials blow up. So, last one. In the same horse race as number 5, oops, that should be number 6, pardon me. Find the number of possible finishes for only the first, second, and third place horses. All right, and we don't care about any of the others. So we only care about 3 of the places. Orders, we don't care about the order of the rest. Try this one on your own, see how you do. Again, this is referring to number 6, of course, not number 5. We're not horse racing around the department store. All right, also if we're ready to continue, here we go. This would be 15P3. We don't want to order all the horses this time. We only care about the first, second, and third place horses, so we only care about 3 of them. And that is going to be a significantly smaller number. It's not a small number by any stretch of the imagination, but it is a significantly smaller number than 1.3 trillion, okay? So about 2,700 options there.